Hi everyone. Today we will discuss about the topic of Hurwitz polynomials. We all know there is a numerator and denominator polynomial in a transfer function, or if you take any other function, whether it is driving point, transfer, or any other system function, there will be a numerator as well as denominator. So each numerator and denominator is nothing but a polynomial in the degrees of s, that is Laplace variable. So now when we can say a polynomial as Hurwitz polynomial. First of all, what is this Hurwitz polynomial? It basically decides the stability of a system, and we all know the importance of stability because it gives the controllability for any system, so that it will not go out of control when we give any input or even for any small disturbance. That is a stable system, and in order to know whether a system is stable or not, we can use the topic of Hurwitz polynomials. And there are certain properties which the polynomial has to follow in order to say that it is Hurwitz, right? Now we will see all those properties. First of all, let us see the definition of Hurwitz. A polynomial is said to be Hurwitz if the following conditions are satisfied. There are only two conditions mainly. The first condition is that polynomial p of s is real when s is real. That means when Laplace variable s is real, your polynomial p of s should also be real. That is first condition. And the next condition is that the roots of p of s have real parts which are 0 or negative. Right? I already told, for stability, the poles of the transfer function must lie on the left side of the system. So in a similar manner, for a polynomial to be Hurwitz, the roots of that polynomial p of s should have real parts which are 0 or negative. Okay, these two conditions are there, but how to check these two conditions? We cannot always substitute all the real parts of s and get the p of s as real, right? It is not possible. So without even determining the roots of p of s, how to know whether the p of s is Hurwitz or not? Because the degree of p of s may be very high. If it is 6, 7 or 8, and we may not have access to any simulation software or coding software in our exams. So manually, how to determine Hurwitz polynomial when the degree is very high, right? It is not possible without any software. So to avoid these two conditions, we can go for other properties. In place of checking these two properties, without checking them, we can check the other properties which are given here, and they are termed as properties of Hurwitz, right? So if you see these, number one property is that all the coefficients in the polynomial p of s should be positive, right? Here a polynomial p of s is given as an example, where it is having the coefficients of an minus 1 and so on, a1 and a0, right? And the degree, highest degree is small n, and the lowest degree is s power 0, that is 1, right? So here all the coefficients, that means an to a0, must be positive. Okay, and if the polynomial is having some missing terms between the highest and the lowest order, all those missing terms should be either all are even or all are odd. Okay, if there is one odd term missing in between, it is not Hurwitz. Similarly, if one even term is missing, it is not Hurwitz. If few terms are missing, all those things should be either even or either odd, right? So that is the first condition. It says 2 points. One point is that all the coefficients should be positive, and also there should not be any missing terms in between the highest and lowest degree, and if suppose they are missing, all those missed terms should be of even or odd, right? Okay, if you see examples it will be very clear. Okay, next, what is the second property? The second property says that the roots of odd and even parts of polynomial p of s must lie on j omega axis only. Okay, we need to consider the separate even or odd terms of the polynomial and then also determine the roots, and if they lie on j omega axis it is Hurwitz. Right? Okay, now the third property is that if the polynomial p of s is either even or odd, the roots of polynomial p of s should lie on j omega axis only. Even the p of s is not even or odd, we have to understand or determine the roots of odd and even parts, and they should lie on j omega axis. And even if the given polynomial is having only even terms or only odd terms, then also the roots of polynomial should lie on j omega axis. Okay, then the fourth property is that all the quotients are positive in the continued fraction expansion of the ratio of odd to even parts or even to odd parts of the polynomial. So I will tell you what is this continued fraction expansion. This is very much useful in the network synthesis topic. This is the first topic where we are going to work with continued fraction expansion. Further, we have several other topics as well. So when you do that fraction expansion, whenever you do fraction, you will get some quotients, right? And those quotients should be all positive in this case. Then only it will be Hurwitz. And fraction should be done either for odd to even or even to odd parts, right? Anything can be fine. Okay, right. Next, the fifth property is that if the polynomial p of s is expressed as a product of two polynomials, that is w of s into p1 of s, then p of s is Hurwitz if w of s and p1 of s are Hurwitz. That means if there is a product of two polynomials which results in another polynomial, for this resultant p of s to be Hurwitz, these individual terms of the product should also be Hurwitz. These all properties are useful somewhere for the problems. We are going to see all those different kind of problems. Okay, right. Then the last property is that if the ratio of polynomial p of s and its derivative p dash of s gives a continued fraction expansion with all positive coefficients, then polynomial p of s is Hurwitz. Right? So here it is a derivative property for the polynomial p of s. What it says, if there is a continued fraction expansion for p of s and p dash of s, it should give all positive coefficients. Okay, otherwise quotients. Positive coefficients are nothing but quotients here. Okay, then also this polynomial p of s will be Hurwitz. Right? So there are 6 properties. Basically it is defined with 2 conditions. To satisfy these conditions, all these properties should be satisfied. Right? When we solve problems, it will be very clear. We will see it in the next lecture. Right? Thank you.